This video shows how to get started with the Qt real-time embedded frameworks and the accompanying suite of host-based tools on Windows. I'll start with downloading and installing the Qt bundle. Next, I'll explain the directories and files comprising the installation. And finally, I'll give you a quick tour of the features. So, starting with downloading and installation, point your browser to state-machine.com and scroll down to the Downloads section. Choose the download for your host operating system, which is Windows for this video. The downloads are hosted on GitHub and contain all Qt frameworks and all the accompanying tools bundled together in a single streamlined installation. Save the Qt bundle installer on your disk. Once the download completes, you can check the executable installer and verify that it is digitally signed by Quantum Leaps. Now you can run the installer. First, you select the install mode. If you have the administrator privileges, it is recommended to install Qt bundle for all users of this computer. Otherwise, the installer offers you an option to install for yourself only. On the introduction screen, just click Next. The licensing agreement screen contains information about the licensing terms of the various components included in the Qt bundle. The Qt frameworks are licensed under the dual licensing model, in which both the open source and traditional closed source software distribution models are combined. For more information about Qt licensing, you can visit the provided link. The QM modeling tool is freeware, licensed under a simple end-user licensing agreement, which you can read at the provided link. Finally, the various third-party tools included in the QTools collection are licensed mostly under the GPL and MIT open source licenses. Some packages, such as Python and Tcl, are licensed under different specific licenses included in the distribution. If you accept the licensing terms, choose the I accept the agreement option and click Next. Otherwise, you can simply click Cancel to cancel the installation. In the next screen, you select the destination location. You could change the provided default, but for the convenience of writing build scripts and makefiles, it is highly recommended to avoid spaces and special characters in the Qt installation directory name. On Windows, this means that you should generally avoid the standard locations like program files or program files open parenthesis x86 close parenthesis. I leave the destination at default and click Next. In the Select Components screen, you can choose the components of the Qt bundle to be installed. The list begins with the QPC, QPC++, and Qt Nano frameworks. You can go ahead and deselect the ones that you are not interested in. The next component is the QM modeling tool, which you should most likely keep. In this Windows installation, you additionally get the GNU CC++ compiler for Windows, the GNU CC++ cross compiler for ARM Cortex-M/R, Python, Tcl, and the Unity unit testing harness. You can deselect any of these components if you already have your own versions or you are simply not interested in a given tool. The next screen offers you an option to add the QTools bin directory to your system path, which is assumed in the Qt examples. Note that all such changes to your environment variables will be reversed when you choose to uninstall the Qt bundle. And so finally, you get to the summary of the installation. Click Install. This takes a minute or two, after which you can view the README file that provides additional information, links, and resources for you to explore. Now let's take a quick look at the main directories and files that have been installed. So, here is the content of the newly created Qt folder in the Windows File Explorer. The first directory inside, QM, contains the QM graphical modeling tool. Typically, you don't need to look inside there, because a shortcut to launch QM has been added to your desktop, and also the model files .qm have been associated with QM, so they will open when you double-click on them. I'll take a little closer look at QM in a minute, but for now let's go back to the QP folder. The next three directories in there contain QP in C, QP in C++, and QP Nano real-time embedded frameworks, respectively. The general structure of all three frameworks is similar, so let me just explain the internals of the QPC subdirectory with the understanding that QP C++ and QP Nano are structured the same way. The third-party directory contains software needed by the embedded boards and the third-party real-time operating systems used in the provided examples. Speaking of which, the provided examples are located in the examples directory. The native examples that use the built-in QP real-time kernels are categorized by the supported CPU, such as ARM7 ARM Cortex-M, ARM Cortex-R, MSP430, PIC24DSPIC, and PIC32. Also here you can find examples for specific third-party RTOS kernels, such as MBOS, FreeRTOS, ThreadX, TiRTOS, and MicroCOS2. Finally, here you can also find QTest unit testing examples, as well as examples that run directly on workstations such as Windows, Linux, or Mac OS. In a minute you will see some of these examples in action. The include subdirectory contains the header files that you need to add to the compiler's include path in your projects based on QP. Similarly, the src directory contains the QP source code that you need to add to your projects to build QP as part of your applications. The ports directory contains the specific adaptations of the QP framework to either the specific CPUs or to the specific third-party RTOSes. The structure of this subdirectory is similar to examples because it reflects the same variety of environments in which QP can run. In your QP-based applications, you will need to add the specific items from the ports subdirectory. For instance, here is the QP port for ARM Cortex-M CPU with the QK real-time kernel built into QP and with the GNU compiler. But going back to the QP folder, the last installed subdirectory, QTools, contains the host-based tools for working with the QP frameworks. Here, the subdirectory bin contains utilities developed specifically for QP, such as QSpy and QClean. But on Windows, you also need general tools such as make and other Unix-style utilities typically used inside makefiles, like makedir, move, movedir, rm, etc. Furthermore, Windows does not provide a standard command line compiler, so the QTools directory contains the MinkW GNU CC++ compiler for Windows. And finally, on Windows you also get the GNU ARM cross compiler, as well as Python and Tcl. For the convenience of using all these tools, the QP bundle installer has added the QTools bin and QTools MinkW directories to your path. And additionally, the installer has also defined the environment variable QTools, which will be useful to build the examples for embedded boards. So now let's take a quick tour of QP and the accompanying tools. Let's begin with examples that don't require any specific embedded hardware because they run directly on your workstation. The simplest of such examples is located in the Blinky directory. On a typical embedded board, this example blinks an onboard LED once per second, but on a workstation it will simply print out the on-off state of the LED. To see how the example works, you open a terminal window and change to the Blinky directory. Next, you will use the make utility from the QTools collection to build the example based on the provided makefile. To execute the build, simply type make. This produces blinky.exe executable in the newly created build subdirectory. You run the example by typing build \blinky. This prints out the changing status of the LED every half second. You terminate the example by pressing Ctrl+C. Now the code for this example in blinky.c has been automatically generated by the QM modeling tool, as this Blinky example actually corresponds to the QM online tutorial. You can double-click on the blinky.qm model file to open it in QM. The whole Blinky application consists of a single active object called Blinky with a very simple state machine. From this model, you generate code by pressing the Generate Code button on the toolbar. Either way, QM regenerates the blinky.c file in this case, but updates it only if it actually differs from the file on disk. The generated code is designed to be highly readable, so you should have no trouble to work with it in a debugger. Also, if you don't like to use QM, you can edit the code manually. But for that, you'll need to uncheck the read-only property set by QM. The next example is a bit more interesting dining Philosophers problem, located in the workstation DPP directory. The DPP example demonstrates multiple collaborating active objects. You build the example exactly as you did before by changing directory to DPP and typing make. When you run the example, it prints out the changing status of the dining Philosophers. You terminate the example by pressing the Escape button. The DPP example also comes with a QM model, which you can open in QM and examine the Philosopher active object and the table active object. As before, you can also generate code for this application. An interesting feature that the DPP example demonstrates is the QPSpy software tracing instrumentation, which is like sprinkling the code with printf statements, only much more efficient and less intrusive. The QPSpy instrumentation is normally inactive, but you can activate it by building the project in the spy build configuration. You select the spy configuration by typing make followed by conf equals spy. This creates the DPP executable in the build_spy subdirectory. Before running that executable, however, you need to open a new terminal window and launch the QSpy utility that is provided in the QTools collection. Only now you can run the spy version of the DPP executable. As you can see, this produces a trace output in the QSpy window. This trace is mostly generated by instrumentation already present in the QP framework itself and is quite valuable for troubleshooting and optimizing your applications. You can learn more about QSpy from the online reference manual. The last QP example on the desktop computer I'd like to show you is a prototype of an embedded board. The example is located in examples ARM-CM game directory and is intentionally co-located with the ARM Cortex-M group because it demonstrates how to run the exact same code on an embedded board and in a Windows prototype. Again, you build the example exactly as before by changing directory there and typing make from the command line. You can also run the example, but this time it is a GUI application in which you can actually play the game almost exactly as you would on an embedded board. The game is about flying a spaceship through a tunnel with mines. You can shoot the mines by pressing button PB0, and you lift the falling spaceship by pressing PB1. This example provides also a solution file for the free edition of Microsoft Visual Studio, which you need to install separately. You can then conveniently develop and debug the code on Windows. The main point here is that you can avoid the embedded hardware bottleneck and develop the bulk of your deeply embedded code, especially the parts related to the user interface, entirely on the desktop machine. To learn more about this approach, please refer to the QWin GUI prototyping toolkit documentation online. Of course, the examples workstation directory contains many more examples that you can explore, including all examples described in the book Practical UML State Charts in C and C++. But now let's move on to examples for real embedded boards. The first such board you could try is the little STM32 NUCLEO L053R8 based on the ARM Cortex-M0 Plus CPU. The DPP example for this board is located in Examples ARM-CM DPP NUCLEO L053 directory. Here you have a choice among the following real-time kernels built into QP: QK preemptive run-to-completion kernel, QV cooperative kernel, and QXK dual mode kernel. Let's say that you are interested in the QXK kernel. You have then further choice of the following embedded toolchains: ARM-Keil, ARM-Clang, GNU, and IAR. Let's say that you pick GNU GCC. You change directory there, and type make. This build uses the GNU ARM toolchain provided in the QTools collection for Windows. Also, the first time the build takes a little longer now because it builds the QP framework from sources, whereas the build for Windows used QP precompiled into a library. Once the build completes, you can check that the binary image has been created in the dbg directory, which stands for debug configuration build. The nice thing about the NUCLEO board is that once you plug it into your computer, it appears as a USB drive to which you can copy the binary image. On my machine, the board appears as the drive F, but of course on your machine the drive letter might be different. Once you program the board that way, it immediately starts running your code. You should see some activity on the onboard LED. But to really see what your code is doing, you could use the QP Spy software tracing introduced before. For this, you need to build the spy configuration by typing make conf equals spy. While this build is executing, you open a new terminal window for the QSpy monitoring utility. However, now you need to connect QSpy to your specific NUCLEO board, which conveniently provides a virtual serial COM port. To open this communication channel, you specify the -C option to QSpy. To find out the specific COM port number, you can open the Windows Device Manager utility. In case of my NUCLEO board, it shows as COM11. Of course, this COM port number might be different on your machine. With this information, you start QSpy with the parameter -C COM11. In the meantime, the build is ready, so you copy the spy binary to the board. When the code starts running, you can see the software trace it produces in the QSpy window. This trace contains both output generated from instrumentation inside the QP framework and output generated by your application. So this was the free command line GNU ARM toolchain. But if you have other toolchains, such as ARM-Keil or IAR installed on your machine, you can find projects for these commercial toolchains as well. For instance, if you are interested in ARM-Keil, go to the ARM subdirectory and double-click on the provided Microvision project file to open it. From here you can build the project and debug it on your target board. You can also build and debug other configurations such as Spy. Of course, I cannot go over all existing examples for other embedded boards and third-party RTOSes, but all of them are structured similarly as the one I just explained. The last thing I'd like you to check out is the QTest unit testing harness, pronounced like the cutest little thing, which is now part of QTools. The specific example for QTest I'd like to show you is the Unity mock example, also explained in the QTest tutorial. This example contrasts two approaches. The standard approach with a traditional Unity testing framework, which requires the mock object test double, and an easier approach with QTest, which allows you to apply a much simpler spy object test double instead of the mock object. The Unity mock example is located in Examples, QTest, Unity mock directory. Here I will only show you the QUTest part located in the test subdirectory. The Unity framework example is located in the test_Unity if you are interested. But for QUTest, you need to change directory to Unity mock test. And also, before running QUTest, you always need to open QSpy in a separate terminal and connect it to the target. First, you will be running the tests on the host computer, for which you don't need to provide any command line options. Now you can simply type make. As usual in unit testing, the provided makefile both builds the test fixture and then runs the tests. As you can see, the tests run and all pass. Now let's test the same COT, code under test, on an embedded board. The test directory provides makefiles for two such boards, EFM32 and TM4C123. Here I will use the TM4C board, also known as the TivaC LaunchPad. As before, when you run QPSpy software tracing on the NUCLEO board, you need to relaunch QSpy to connect to the embedded target. Again, as before, you can open the Windows Device Manager to find out the COM port number of the board. With this information, you can launch the QSpy with the -C COM7 option. Now you can build and run the tests on the board by typing make -F followed by the makefile for the board. This builds the embedded code with the GNU ARM compiler, loads it to the flash memory of your board, and runs the exact same unit tests as before on the host. As the last exercise, you can modify your test to see how it fails. The QUTest tests are written in Python and you can very quickly edit them on the host. For instance, to break one of the tests, let's modify the expectation in the third test from LED off to LED on and save the file. Now you can just revoke the make command and immediately run the tests again. Please note that there is no need to recompile the test fixture or download it again to the target. All such changes are handled on the host. You can also easily see where the test fails and which line caused the problem. This concludes this quick tour of QP and the accompanying suite of host-based tools. To get started with QP quickly, I'd like you to remember that in embedded systems, nothing works until everything works. This means that the easiest way is always to start with one of the working examples. It is highly recommended that you simply buy one of the very inexpensive evaluation boards we support, even if it is not exactly your final hardware, and use it to run the provided example projects before making any changes or trying to use your own target hardware. Thanks for watching.